Concentration is a method involving quantifying amounts of solute per amounts of solvent or solution. In this class, there are four main ways we are going to express concentration. One is mass percentage, 2 is molarity, 3 is molality, 4 is mole fraction. Mass percentage or percent mass is very similar to percent composition. We take a part to a total and multiply by 100. So when we do mass percentage, it is going to be mass of solute over the mass of solution times 100, in which you know the mass of the solution is equal to the mass of solute plus the mass of the solvent, because solution consists of two parts, the solute and the solvent. Another way to express mass percentage is parts per million. Parts per million, ppm, is equal to mass of solute over mass of solution. Again, mass of solution is mass of solute plus mass of solvent. But since it's parts per million, we multiply by 10 to the 6, which is a million. We can also express mass percentage as parts per billion, ppb, which is equal to mass of solute over mass of solution times 10 to the 9th, which is a billion. So these formulas are very similar to each other, except for parts per million, we multiply by a million, and parts per billion, we multiply by a billion. Pause the video, try this problem on your own, and then check your answer. What is the mass percent of each component in the mixture formed by adding 12 grams of calcium sulfate, 18 grams of sodium nitrate, and 25 grams of potassium chloride, and 500 grams of water? So in this problem, I need to find mass percent, which is equal to the mass of solute over the mass of the solution times 100. The mass of the solution here is composed of all the solutes. So it's going to be the mass of the calcium sulfate plus the mass of the sodium nitrate plus the mass of potassium chloride plus the mass of the water. So this is going to equal to 12 grams plus 18 grams plus 25 grams plus 500 grams. This equals to 555 grams with correct sig figs. The least precise position is the ones place, so it's going to be rounded to the ones place. So we have to find the percent mass separately for each of the components. Percent mass of calcium sulfate is going to be the mass of calcium sulfate, which is 12 grams over the total, which is 555 grams times 100. This equals 2.16, but with correct sig figs, because the 12 has 2 and the solution has 3, so the least amount is going to be 2. We go 1 to the right, so this becomes 2.2% of calcium sulfate. We'll repeat it for the other ones. So this is mass of sodium nitrate, which is equal to 18 grams over 555 grams of solution times 100. This equals to 3.24. Again, there's 2 sig figs for 18, 3 for the denominator, so least amount, so I need 2. 1, 2, I look 1 to the right. That becomes 3.2% of sodium nitrate. We're going to repeat the procedure for potassium chloride, which is mass percent of calcium. Potassium chloride is going to be the mass of the solute, which is 25 grams of potassium chloride, over the total mass times 100. This equals to 4.50. This one also has 2 sig figs, 2 from the solute, 3 from the denominator. So least amount, so 1, 2, I look to the right, it stays 4.5% of KCl. And we need to calculate for water, percent mass of water. This one had 500 grams over the total times 100 equals to 90.09. 3 sig figs on top because there's a decimal and a significant digit in front. 3 in the denominator, so I need 3 in my answer. 1, 2, 3, I look 1 to the right. This becomes 90.1% of water. The other way you could have solved the last component, it has to equal to 100%. You could add the other 3 and subtract from 100%, or you could just plug it into the formula. If you did the math correctly, at the end, if you add all the percentages, they should equal to approximately 100%. Pause the video, try this problem on your own, and then check your answer. A solution is made by adding 25 ml of benzene to 80 ml of toluene. What is the percent by volume of benzene? This problem is very similar to mass percent. Mass percent is a ratio. We know mass percent is a ratio because the formula is mass of solute over mass of solution times 100. Since it's a ratio, as long as the units are the same, the units will cancel out. Remember, ratios have no units. So we could also rewrite this equation as percent volume. So instead of having mass, we're going to have volume of solute over volume of solution times 100. As long as the units of volume are in the same unit, the units will cancel out. So here we have 25 ml of benzene that is going to be added to the toluene where there's 80. So that tells you the benzene is my solute, my toluene is my solvent. So we are looking for the benzene, so we know the volume of the solute. The volume of the solute is going to be 25 ml. My volume of the solution is the volume of the solute plus the volume of the solvent. So this is going to be 25 ml plus 80 ml times 100, which equals 23.80. So now I need to do sig figs. So for 25, there is 2 sig figs. If I add 25 to 80, I need to line up the decimal. This is going to be 105. So I'm going to round here. So there's going to be 2 sig figs. So my final answer is going to be the least amount, which is 2. So it's going to be 1, 2. I look 1 to the right. This is going to be 24% of benzene. Pause the video, try this problem on your own, and then check your answer. An experiment requires a solution that is 80% methyl alcohol by volume. What volume of alcohol should be added to 200 ml of water to make the solution? So we know the solute is going to be methyl alcohol because this is being added to the water, so the water is my solvent. So we are looking for what volume of the alcohol. So we're looking for the volume of the solute. This is what we're looking for. Since it's a percent volume, my formula is going to be percent volume is equal to volume of my solute divided by my volume of solution times 100. So if you're struggling here, identify your variables. We already know we're looking for the volume of solute. We know the percent volume, and my percent volume here is going to equal to 80%. The volume of the solution is going to equal to the volume of the solute plus the volume of the solvent. So if I replug this in, this becomes percent volume of solute over volume of solute plus volume of solvent times 100. So in this problem, I cannot leave the volume of solution as 1. I need to separate it as volume of solute plus the volume of solvent because I do not know the total volume of the solution. Since we are looking for the volume of solute, I need to isolate that variable. I'm going to cross multiply, and I'm going to rewrite the 100 as my numerator because that's what it is. And so if I cross multiply, the percent volume denominator is a 1. So these are going to be cross multiplied. This is going to be percent of volume multiplied by the volume of the solute plus the volume of the solvent. This is going to equal to 1 times volume of the solute times 100. So at this point, for most of you, it's going to be easier if you plug in some of the numbers to simplify, because it will cancel out some of these symbols that are present. We know the percent volume is going to be 80%. That was given. That's going to be multiplied by the volume of solute because we do not know what that is. We know the volume of solvent is given as 200 mLs right here, which is the water. This is going to equal to 100 times the volume of solute. Next, I'm going to distribute the 80%. So if I distribute the 80%, it's going to be 80% times V solute. So that's going to be 80 times V solute plus 80 times 200. So 80 times 200 is 16,000. This is equal to 100 V solute. Now we're going to put all the V solute on the same side. So I need to subtract by 80 V solute because it's added to the 16,000. And I need to subtract 80 on the opposite side because we need to do the same in math. The 80 on the left side cancels out. So we end up with 16,000. And on the right side, 100 minus 80 is 20 V solute. Next, we're going to isolate V solute by dividing both sides by 20. So V solute equals to 800 milliliters. Pause the video, try this problem on your own, and then check your answer. Here we have 2.5 times 10 to the negative 4th grams of helium gas that is dissolved in 200 grams of water. Express your answer in parts per million. Here the gas is your solute because it's being dissolved in 200, which is your solvent. We're looking for parts per million. Parts per million is equal to mass of solute over mass of solution times 10 to the 6th. Substituting in for mass of solution, this is mass of solute over the mass of solute plus mass of solvent times 10 to the 6th. And again, you could solve for the mass of solution outside and then plug it in. Either way, it's okay. So my mass of solute here is 2.5 times 10 to the negative 4th grams. And this is my helium gas. And I'm going to plug in on the bottom for mass of solute, which is 2.5 times 10 to the negative 4th grams of helium plus 200 grams of water times 10 to the 6th. If you do your math correctly, you get 1.2499. And if we have to do sig figs, there is 2 on top here because exponents do not count. Everything in front counts. For the denominator, we're doing 200 grams. I'm going to add, if I convert this, this is 0.00025. So 0.00025. So if I add this, I'm rounding here at the 10th place. So if I round it to the 10th place, this one's going to have 4 significant digits. Because if I add this, this becomes, and so there's 4 significant digits. So it's the least amount, so I need 2. So this is going to be 1.2 parts per million. Pause the video, try this problem on your own, and then check your answer. Here we have a solution of lead sulfate. It contains 0.305 grams of the lead sulfate in 500 grams of water. what is the concentration in parts per billion? Since we have lead sulfate in water, my lead sulfate is my solute here, and my solvent is my water. So parts per billion is going to be mass of solute over mass of solution. Since we know the solution is given as mass of solute plus mass of solvent, I'm going to already write that in. It's going to be mass of solute plus mass of solvent times 10 to the 9th because it's parts per billion. And all I'm going to do is plug in. So mass of solute is the lead sulfate, so it's 0.305 grams over 0.305 grams plus my solution, which is 500 grams, times 10 to the 9th. If you plug this into the calculator, you should get something like this. So now if I do sig figs, the lead sulfate, there are 3 sig figs. So if I add the denominator together, I need to line up the decimal. But the least precise position is right here. So if I actually add this, this is my answer. So I'm going to have 4 sig figs. The least amount is going to be 3. So 1, 2, 3. I look 1 to the right. This is going to be 6. 1, 0, because I have to carry the 1 over. 0, 0, 0. This 0 is significant, so I have to write this in scientific notation. This is going to be parts per billion. If you put a decimal here, if you put a decimal anywhere along this, it will make all the zeros significant. So that means you're going to have 6 significant digits. So to avoid that and make it 3, I write it in scientific notation. Pause the video and try this problem on your own and then check your answer. Here we have a concentration of Cl- ion in a sample of water that is 15 parts per million. What is the mass of the chlorine ion present in 240 milliliters of water, which has a density of 1 grams per ml? So we know it's going to be the parts per million equation because that's what's given. So parts per million is going to be equal to mass of solute over the mass of solution, which I'm already going to substitute in because I don't know the mass of the total solution. Since I don't know the mass of the solute, this is going to be mass of solute plus mass of solvent times 10 to the 6th, because this is parts per million. Cl minus is my solute. The mass of solute that I am looking for here is my Cl ion. You don't know this. This is a Cl minus ion. So I also need the mass of my solvent here. Mass of my solvent is not given to me, but I know the volume of my solvent, and I also know the density of my solvent. So I'm going to solve for the mass of the solvent using stoichiometry. I'm going to start with 240.0 mLs. Diagonal units have to be the same. This is ml. This is ml. This is 1 ml to 1.00 grams of water. So this equals to 240.0 grams of H2O. Density is a conversion factor. If I have a density that is 1.0 grams per ml, this is the same thing as rewriting this as 1.00 grams of water is equal to 1 ml. So what that means is in 1 ml, a volume that is 1 milliliters, there's going to be 1 gram of water. We also know our parts per million, which is equal to 15. So what I need to do is I need to isolate my variable mass of solute. So I'm going to rewrite the equation and solve for the mass of solute. So we know it's going to be parts per million. I'm going to rewrite the numerator so it's mass solute. This is going to be times 10 to the 6th, and it's going to be divided by mass solute plus mass solvent. And first thing I'm going to do is I'm going to cross multiply. So the parts per million, the denominator is 1. I'm going to cross multiply. So that means parts per million. This is going to be mass of solute, which is the Cl minus ion, plus the mass of the water, which is my solvent. This is equal to the mass of my Cl minus ion times 10 to the 6th. At this point, for most of you, it's going to be simpler if you plug in some of the numbers. so you could get rid of a lot of these variables. My parts per million is 15. We identified these variables earlier. The mass of the chlorine ion I am looking for. My mass of water, I solved that to be 240 grams using dimensional analysis. This is going to be equal to, again, the mass of the chlorine ion times 10 to the 6. Next, I am going to distribute the 15 on the left side. It's going to be distributed this way. So if I do my multiplication, it's going to be 15.0 times mass of chlorine plus 3600 equal to 10 to the 6 mass of the chlorine ion. Now I need to isolate the mass of chlorine ion by subtracting 15 on both sides. So my equation becomes 300. 10 to the 6 minus 15 is pretty much 10 to the 6 mass of chlorine ion. So now I'm going to divide both sides by 10 to the 6, isolate mass of chlorine ion. So mass of chlorine ion equals to 0.0036 grams of chlorine ion. If you're struggling with the algebra, isolate the variables as much as possible, plug in the numbers to simplify it, and then double check your answer. Molarity, capital M, is the most concentration expression you will see in the upcoming chapters. Molarity is equal to the moles of solute over liters of solution. If I condense it into a simple formula, it is capital M, which is equal to moles over volume. Remember, the volume must be in liters. The unit are moles per liter, or the SI unit is molar, which is abbreviated capital M. Molarity is temperature and pressure dependent. So that means if the temperature or pressure changes, the molarity will also change. Pause the video, try this problem on your own, and then check your answer. There is 952 grams of ammonium carbonate dissolved to make 1750 milliliters of solution. Determine the molarity. Formula for molarity is capital M, moles of solute, over liters of solution. My solute here is ammonium carbonate. Since it's in grams, the first thing I need to do is convert my grams into moles using molar mass. I'm going to put everything in the problem itself. Again, you could do each of these steps separately and then plug it in to the equation. So I'm going to start with 952 grams ammonium carbonate. Ammonium is NH4, charge is 1. Carbonate is CO3, charge is 2 minus. I can't reduce, so now I crisscross down. So it becomes NH4. I need the parentheses 2 because there's more than one polyatomic. CO3. This is going to be NH4 to CO3. Converted, diagonals have to be the same, so this is going to be grams of NH4 to CO3 to 1 mole of NH4 to CO3. The molar mass, 96.09 grams. The liter of solution is given in milliliters, so I need to convert that. So I start with milliliters. Milliliters, 2 liters, 1 liter, 1000 milliliters. Cancel out and do all your math. You should get something like 5.6613. This is a conversion factor, so it doesn't count. So there is 3 here. This is a conversion factor, it doesn't count. And there's 3 here. This is a trailing 0 because there is no decimal, but there's only a significant digit. Remember, you need to have the decimal and significant digit to make it significant. So my final answer has 3. 1, 2, 3. I look 1 to the right, so it's 5.66. You could use moles per liter or molar. Pause the video, try this problem on your own, and then check your answer. How many grams of calcium hydroxide are needed to produce 500 ml of a 1.66 molar calcium hydroxide solution? So if I identify the variables, we are looking for mass, which we don't know. My volume of solution is 500 ml, and I know molarity is equal to 1.66 molar. My formula for molarity is moles of solute, which is my calcium hydroxide, over volume of solution. So if I find the moles of the solute, I could find the mass of calcium hydroxide using molar mass. So if you're struggling with math, the first thing you want to do is isolate the variables. So you want to multiply both sides by the volume. The volumes cancel out. That means the moles of solute is going to equal to mass times volume, equal to molarity times volume. If I plug my numbers in, this is 1.66 molar. My volume is in milliliters, so I need to convert it. Milliliters, milliliters. There's 1,000 milliliters in 1 liter. If you calculate this correctly, you get approximately 0.83 moles of solute. My solute is calcium hydroxide. So now I start with 0.83 moles calcium hydroxide. Diagonals have to be the same, and I'm going to do molar mass. Solve for the grams. So there's 1 mole. The mass of calcium hydroxide is 74.093 grams, and you get approximately 61.497. So now we go back and do sig figs. Since everything is multiplied and divided, there is 3 here. There's 1 here. This doesn't count. That's a conversion factor. And this doesn't count. That's a conversion factor. So my answer is 1 sig fig. So 1, I look to the right. So it becomes 60 grams of calcium hydroxide. The easier way to do this is just set it up as a dimensional analysis problem. When something is written as 1.66 molar, that's the same thing as 1.66 moles per liter. So it's just a conversion factor. It tells you that I have 1.66 moles, in this case solute, of calcium hydroxide in 1 liter of solution. So it becomes a conversion factor. So I would start with my volume, which is 500 ml. That needs to be converted to liters because my conversion factor is in liters. So milliliters, there's 1,000 milliliters in 1 liter of solution. My milliliters cancel out. This is liters. This has to be liters. There's 1 liter of solution, and that is equal to 1.66 moles of calcium hydroxide. The moles, diagonals have to be the same. Moles of calcium hydroxide, there's 1 mole, and the molar mass of that is 74.093 grams of calcium hydroxide. So if you do the math, it will come out to the same answer. I think the second method is a lot faster than the top method, but either way works, just do the math correctly. Pause the video, try this problem on your own, and then check your answer. A commercial concentrated aqueous ammonia is 28% by mass and has a density of 0.90 grams per ml. What is the molarity of the solution? So we are given 28%, so we know this is a mass percent. That's 28%. We are also given a density. This density is the density of the solution, which is equal to 0.90 grams per ml. We're looking for molarity. So now let's write the formula because we need to figure out what variables we need to go from the given, which is percent mass, to molarity. So we know the formula for percent mass is equal to mass of solute over mass of solution times 100. The formula for molarity is moles of solute over liters of solution. So what we need to do is we need to find the mass of the solute, because if I know the mass of the solute, I could convert it into moles of solute using molar mass. I could also convert my mass of solution to volume of solution using density as a conversion factor. So how do I do this when I don't know the mass of the solute, I don't know the mass of the solvent, and I don't know the mass of the solution? When I am given 28% of NH3, I know my NH3 is my solute. Since it's given in percentage, I could write this as there are 28 grams of solute NH3 to 100 grams of solution. The reason I could do that is 28% is part, the whole is 100%. Since it's a ratio, 28 grams over 100 grams can also be written as 28 grams of liter over 100 grams of liter, and so forth. But we want it in mass because we have density and we need the mass to convert to moles. So now that we know there are 28 grams of NH3, we could do molar mass. Here, I'm going to plug it all into the equation. However, if you want to do it separately and plug it in, you are welcome to do that. So there's 28 grams of NH3. And so grams of NH3, I need to convert it to moles. There's 1 mole of NH3, 17.03. Now I'm going to convert my solution, which is in mass, to volume. To do that, I'm going to use my density here. We stated that if we have 0.90 grams per milliliter, this is the same thing as rewriting this as a conversion factor as 0.9 grams is equal to 1 milliliter. I'm going to start with 100 grams of solution. Diagonals need to be the same. So this is grams. The number in front of grams is 0.90. And this is equal to 1 ml. These are equivalent. What it's saying is in 1 ml or 1 milliliter volume, there is a mass of 0.90 grams. Now I need to convert my milliliters into liters because molarity is in liters. There's 1,000 mLs to 1 liter. So if you plug all of this in, you get 14.797. So now let's do sig figs. There's 2 sig figs here, conversion factor. This is 100 is one we just wrote in, because we could write the 100 as 100 decimal and so forth. So we're just going to use the 2 sig figs because that is what we depended everything on. And 0.90 is a conversion factor. So that's 1, 2, I like 1 to the right. So this is 15 molar or moles per liter. Molality is another expression for concentration. It is little m. Molality is equal to moles of solute over kilograms of solvent. Please note, between molarity and molality, it differs by 1 letter. Molarity is a capital M. Molality is a little m. So if I cannot differentiate between a capital and a little m, I'm going to mark it wrong. So make sure you write it correctly. The units of molality is moles over kilograms here, or molal, which is the SI unit abbreviation M. This is not dependent on temperature or pressure, unlike molarity. Pause the video, try these problems on your own, and then check your answer. This problem is pretty straightforward. We have 7.45 grams of potassium chloride was dissolved in 100 grams of water. Calculate the molality of this solution. General formula for molality is little m, which is moles of solute divided by kilograms of solvent. My solute is my potassium chloride because that was being dissolved. My water is my solvent. Since the solute is given in grams, we need to do molar mass to find the moles. Since the solute is given in grams, we need to use stoichiometry and molar mass to calculate the moles. So you could do these steps separately or plug in all at once like I'm going to do it. So we're going to start with 7.45 grams of KCl because that is my solute. I'm going to do dimensional analysis to convert it into moles. So grams, KCl, diagonals have to match. This is equal to 1 mole of KCl. Molar mass is 74.55 grams. Grams of KCl cancel out. So I have moles of solute on top. On the bottom, it has to be kilograms of solvent. Water is my solvent. It is in grams, so I need to convert this into kilograms. So grams, 1,000 grams of water and 1 kilogram of water. 0.99932. We're going to go back and do sig figs. These are conversion factors, so they don't count. There's 3 here. The 100 has 1 sig fig, so my final answer has 1. 1, I look 1 to the right, so this becomes 1 molal, or moles per kilogram. Pause the video, solve this problem, and then check your answer. There is 11.11 grams of urea that was dissolved in 100 grams of water. You need to calculate the molarity and molality of the solution. So first, you need to identify the solute, solvent, or solution. Here, my solute is my urea because it's being dissolved into. Water is my solvent. So the first thing I'm going to do is I'm going to solve for molality. So molality, little m, is equal to moles of solute over kilograms of solvent. So moles of solute, I have to convert the 11.11 grams of urea to moles by using molar mass. There is 60.06 grams of urea in 1 mole of urea. Kilograms, there's 100 grams of water. You need to convert that into kilograms. There's 1,000 grams in 1 kilogram. It equals 1.8498. If we do sig figs, there are 4 here. This doesn't count conversion factor. There are 3 here because there's a decimal and a significant digit in front, and that doesn't count because it's a conversion factor. My final answer has 3. 1, 2, 3. I look 1 to the right, so it's 1.85 molal, little m, or moles per kilogram. So now let's solve for molarity. Molarity is going to be moles of solute again, but this one is going to be liters of solution, or volume of solution. You know how to find the moles of solute. I'm going to do the same as we did above. Molar mass. Again, you could do the molar mass outside and plug it in. That's fine. In this case, it will be a little bit faster because you don't have to write it down twice. Liter of solution. So my solution, I need what? My solute and my solvent. Both my solute and solvent is given in grams, so technically we're going to have the mass of solution. My mass of my solute is 11.11 grams. My mass of solvent is 100 grams. So if I add it together, this is going to be, it's going to be 111.1111, but with correct sig figs, it's going to be 111 grams. Since we need the liters of solution and the density of the solution was not given to convert my grams into liters, we're going to just assume that the density of the solution is very similar to the density of water. And density of water is 1 gram per ml. Written as a conversion factor, it tells you there's 1 gram water in a volume that is 1 milliliter. So my mass of the solution is given as 111 grams. This is my solution. I need to convert this into milliliters because we want liters, or volume of solution. So that's going to be 1 gram because this is 1 gram right here. This is equivalent to 1 ml. The grams cancel out, but we need the milliliters to be converted into liters. That's 1,000 milliliters to 1 liter. This equals 1.6665. Now working on the sig figs, there's 4 here. Conversion factors doesn't count. There is 3 here. These are all conversion factor. My final answer has 3. 1, 2, 3. I look 1 to the right. This is 1.67 molar, or moles per liter. There are 3 areas you're going to struggle with. One is identifying what is the solute, solvent, or solution. Remember, the solute is always the one that is being dissolved. The solvent is always the one doing the dissolving. The solution is always the solute plus the solvent together. Next, if you're struggling with algebra, isolate the variables before you start plugging in number. The area that is going to give you the biggest difficulty is when the mass of the solute and the mass of the solution are not given at the same time. And last, make sure you plug into the calculator correctly. Use the EE button for exponents.